Hello, welcome to our class today. We continue with our lessons in programmable mathematics. We were looking at fields, prime fields, and today we want to look at a very important concept in prime fields, the concept of quadratic residues and non-residues. So what we need to know is what are quadratic residues and what are quadratic non-residues, so that whenever we meet these terms, we know what they mean. And they're very important for us in number theory, they're very important in cryptography, and so many other areas of security. Now, so a quadratic residue, when we talk about given a field, and then we talk of quadratic residues, we just mean what numbers have square roots. That's what we mean. What numbers have square roots? And as I've said, that if you're given a field f of p, where p is prime, and it's an odd prime, p should be an odd prime, because we know that 2 is a prime number, but 2 is not, cannot be p. So p should be an odd prime. So for instance, p could be 3, p could be 5, could be 7, 11, and so on. So those are the numbers we're referring to, prime numbers. So we are saying, for instance, if you're given f of 7, so just asking ourselves, what numbers have square roots here? F of 7 includes numbers 0, 1, 2, 3. No, okay, yes, up to all the way up to 6. This is f of 7. Field mode 7. So which numbers have square roots? And what we note is that between 0 and 6, the numbers that will have square roots will be a half of these numbers. And a half of these numbers will lack square roots. So those that lack square roots, we call them quadratic non-residues. Half of them, if you're given p, then a half of p would have square roots, and a half will not have square roots. Mod p. So we're talking about mod p. That's what it means. So quadratic residues then are those numbers that have square roots. So they are squares. Those numbers are squares. They have square roots. And quadratic non-residue are those that lack square roots. So that is what my definitions mean. So this definition said an element R is called a quadratic non-residue if it has no square root. That is, if you cannot obtain another number x, that when you multiply this x, you get a. If you cannot get an x which, when it's squared, gives you a, then this a is quadratic non-residue. In other words, it has no square root. That's what those terms mean. So they don't mean anything else. They just mean numbers that have square roots and numbers that do not have square roots. So those that have square roots, we call them quadratic residues. And those that lack square roots, we call them quadratic non-residues. And I've said, if you're given p, then a half of the numbers mod those numbers mod p will have square roots, and a half would lack square roots. So those are the properties I'm referring to here. So the properties, I'm just saying that the first quadratic residue of the numbers will be 0. 0 will be a quadratic residue because it has a square root. 0 has a square root. And the square root of 0 is 0. So that if you have 0 squared, gives you 0. So 0, therefore, is a quadratic residue. Is a quadratic residue. It has square root. That's the first number. We shall check other numbers as we go along. Given mod something, we'll be checking to see which ones have square roots, which ones do not. And of course, this concept, we'll see how it's important to us going forward. Now, I've said a half of the non-zero elements, f of p, that is a field mod p, would be quadratic residues. In other words, we'll have square roots. And then the remaining half would lack square roots. Would lack square roots. So if our p is 7, so just saying, how many numbers do you have? 0, 1, 2, 3, 4, 5, 6. Yeah, we have those numbers, 6 numbers. Just saying that, no, these are 7 numbers. But this one is already a quadratic residue. This 0 is already a quadratic residue. So I've just said a half of the non-zero. The ones left, there are 6 of them. These 6 of them, 3 of them would have square roots, and 3 would lack square roots. So that's the formula. The easiest formula is just this. That p is 7, subtract 1 from it, divided by 2, you have 6 divided by 2, which is 3. In other words, 3 would have square roots and 3 would lack square roots. But 0, we've already said it has square root. So it's a quadratic residue already. So we're just interested with what is left. 3 of these have square roots also. So which ones are they? That's what we'll be looking at. That's what we'll be looking at to find out how many and which ones have square roots and which ones lack. And of course, the term I want us to just use is the term quadratic residue and quadratic non-residue, so that get to use those terms. As we proceed forward, we'll be using those terms. And of course, we know what they mean. Now, the other property I've just said that if you have 2 quadratic residues and multiply them, the result will also be a quadratic residue. In other words, if you have 2 numbers whose square root you can obtain, if you have 2 numbers whose square root you can obtain, multiply those 2 numbers, and the result will give you a number whose square root you can also obtain. Just a simple, although this is not the best example because we are supposed to use p. P is supposed to be prime. But a very easy example, 4, we know this, it has a square root, and 9 also has a square root. So you're saying that the product of these 2 will also have a square root. The product of these 2 will also have a square root. That is what this is saying. The product of 2 quadratic residues, and I've said this is not a best example because, okay, it's a good example. If we can say mod, if I say I'm doing mod 13, I'm saying I'm doing, if this is my f mod 13, then it becomes a very good example. Yes, now let me say I'm doing it mod 13. So of course I know this number is here and this number is also here. So this number has a square root and this number also has a square root, mod 13. So when you multiply these 2 numbers, what you get mod 13 will also have a square root. Of course, it's not necessarily 36 because we shall have to reduce it to mod 13. But whatever you get will have a square root. That is what this property is saying. That if you have 2 numbers which are quadratic residues, their product will also be quadratic residue. And if you have 2 numbers that have no square roots, if you have 2 numbers that have no square roots and multiply them, they'll give you a number that has a square root. They'll give you a number that has a square root. That's what this one is saying. So the product of 2 quadratic non-residues is a quadratic residue. What about if you take a number that has a square root and a number that has no square root? and multiply them, the result will be a number that has no square root. So a quadratic residue times quadratic non-residue gives you a quadratic non-residue. And again, we'll be seeing how this then is applied going forward. But before we see the application, there's something very much related to this, what we call the Lagrange symbol. And what does it say? It gives us an easy way of determining numbers which are quadratic residues and numbers which are quadratic non-residues. So it's an easy way of identifying numbers that have square roots and those that have no square roots. What does it say? To determine whether a number R in f of p is a quadratic residue or a quadratic non-residue, we use this Lagrange symbol. And what does it say? That A, this is just a symbol. It's not A out divided by B, but it's just the Lagrange symbol of A will be 1. This will be 1 if A is a quadratic residue. If A is a quadratic residue, then you get 1. I'll show you how we obtain this. It's not necessarily division. It's not necessarily division. I'll show you what it is. So that's why I said we don't say A divided by P. It's not the case. We're just saying the Lagrange symbol of A. If the Lagrange symbol of A is 1, then that A becomes a quadratic residue. And if the Lagrange symbol of A is -1, then A is a quadratic non-residue. But if the Lagrange symbol of A is 0, then it means that A is 0. It means that A is 0. And of course, if A is 0, then we know that A is again a quadratic residue. Now, so therefore, I want to show you how to do the Lagrange symbol and then use it to tell that a number is a quadratic residue or quadratic non-residue. But before that, we can just take a simple example to determine if a number is. So let me say, for instance, I want to determine numbers which are quadratic residues, mod 7. I know what the numbers mod 7 are 0, 1, 2, 3, 4, 5, then 6. These are the numbers. I want to call these numbers the square roots. I want these to be the square roots. Square roots. So let me just square them and see what I get. What I get is the number, the quadratic residues. For instance, if I square 0, I get 0. If I square 1, and remember I'm doing it mod 7, this gives me 1. This gives me 4. This gives me 2. Is that okay? 3 times 3 will be 2. Mod 7. And this is 16 minus 14, and again that is 2. And this will be 25. 25 minus 21, that would be 4. And this will be 36 minus 35, and that will be 1. So what does my table mean? My table means that whatever is at the bottom here has square root. For instance, 0 has a square root. What the square root of 0 is 0. The square root of 1 has a square root. So the square root of 1 is 1 or 6. 1 or 6, you can see. When you square 1, you get 1. When you square 6, you get 1. And I'm doing that mod 7. The square root of 4, I've found it that it's 2 or 5. So the square root, you see, you can have, a number should have 2 square roots. That is why every time we're getting square root, there are 2 numbers. The square root of 2, and you can see the square root of 2 here is 3 or 4. So what are quadratic residues? So the quadratic residues, mod 7 in F7, there are 0 is a quadratic residue, 1 is another, 2 is another, and then 4 is another. The rest are not. The rest are not. For instance, you cannot get a number which when you multiply gives you, when you multiply by itself, gives you 3, mod 7. That number is not there. That number is not there. So the quadratic residues mod 7, therefore, are these. These are the quadratic residues. And the quadratic residues are these. That's why I said of the non-zero numbers, half of them will be quadratic residue. And you can see the non-zero numbers are 1, 2, 3, 4, 5, 6. Half of them are 3. Those 3 are quadratic residues. And a half, again, 3 are quadratic non-residues. Now, I don't know whether you understood this simple way of getting quadratic residues. I just want you, first of all, to understand what I mean. Then before we go to the Lagrange symbol, how to use it to determine if numbers are quadratic residues or quadratic non-residues. Okay. Now, so we just mean which numbers have square roots. Which numbers have square. So my example, I just worked with the numbers and I was finding their squares, first of all. I find the squares of these numbers, the numbers at the bottom. So the square of 0 is 0, the square of 1 is 1. That means 1 has a square root. One of the square root is 1. Because when you square 1 times 1 gives you 1. And then the square of 2 is 4. That means 4 has a square root. And the square root of that 4 is 2. And we look for another one will be found. And you can see that 3 square gives you 2. That means 2 has a square root. And one of the square root is 3. Because 3 times 3 will be 9. And we are doing this mod 7. So if there are new people, this means, why I got this, why I was getting this number. 3 times 3 gives me 2 because we divide 7 into this and then write the remainder. So the remainder is our result. That's when we're talking about mod 7. We talk of mod 7, it means write the remainder after division by 7. So 9 divided by 7 is 1, but the remainder is 2. So that's what we are doing here. That is the same thing you can see me do here. 5 times 5 will be 25, but we are dividing by 7 and writing the remainder. So when you do this, 7 goes 3 times, and is it 3? Yes, 3 because of 21. When you subtract 21 from this, the remainder is 4. So that is. So again, 4 has a square root. That's what it means. The square root of 4, one of them is 5. Good. So that is what you mean by quadratic residues and quadratic non-residues. The quadratic residues are those integers that have square roots. And there are other integers that have no square roots. We call them quadratic non-residues. So you can follow this other example. If P is 13, we are trying to find what are the quadratic residues. I just took the elements mod 13 and squared them. 0 squared will be 0, 1 squared will be 1, 2 squared will be 4, 3 squared will be 9, and 4 squared will be 3. And again, for the new ones who are here, 4 squared, of course, you know it's 16, but we are doing it mod 13. You're doing it mod 13. That means you are dividing by 13 and writing the remainder. That's what you see there. And the 5 square again will be 12 using the same method. Because it will be 25, but you are doing it mod 13. So divided by 13 and you write the remainder. 6 square will give us 10. 7 square will be and so on. So what that therefore means that these numbers at the bottom are the ones that we call quadratic residues. They have square roots. You can see 0 has a square root there, 1 has this square root, and the other square root is here, 12. 4 has this square root, and the other square root of 4 is 11. Of course, we know even from the normal mathematics, the square root of 4 is supposed to be plus or minus 2. But minus 2 mod 13 is 11. No, yes, no, you're doing it. Yes, you're doing it mod 13, so it's 11. That's why you find that the square root of 4 is 2 or minus 2, which is 11. 2 or minus 2, which is 11. The square root of 9, of course, we know. The square root of 9 will be plus 3 or negative 3. So plus 3 or negative 3, but negative 3 mod 13 is 10. Negative 3 mod 13 is 10. So just take it through negative 3 and adding 13 to it until you get a positive number. That's what we mean. And that's the same thing we did here. When you had the negative 2, we just added 13 and got 11. So those numbers at the bottom are quadratic residues. And you will find that they are 13 minus 1 divided by 2. 13 minus 1 divided by 2. Then you add that is 0. So what do I mean? How many are they? That's the question I'm answering. How many are they? How many quadratic residues do you have? Just saying the quadratic residues will be 13 minus 1 divided by 2. And this is 12 divided by 6. There are 6 of them. Then you add the 0. So 1, 2, 3, 4, 5, 6, then 0. But these others will just be 6. 1, 2, 3, 4, 5, 6. 13 minus 1 divided by 2. And that is now the formula. I'm trying to look at the formula for using for Lagrange. No, Legendre symbol. The formula for the Legendre symbol is the one I'm trying to come up with so that we now look at it, the next example. So the Lagrange symbol is here. It's telling us what is happening here. I'm asking myself, is 1 a quadratic residue? Is 3 a quadratic residue? Is 4 a quadratic residue? Is 9? So from this, what we've just done above, we found that 1 is a quadratic residue. So that means the Lagrange symbol, 1 out of 13, is supposed to give us 1. And I said this is not division. And again, 4 out of 13, the Lagrange symbol of 4 is supposed to give us 1. What about those that are not giving us, they're not here, like 2 is not here, 2 is not here. So the Lagrange symbol of 2 will be negative 1. And the rest will be negative 1. So how do we calculate the Lagrange symbol? So to do that, we use the Euler's criterion to calculate what I've just calculated here. We use the Euler's criterion. And what does this Euler's criterion say? The Euler's criterion says that if you take a number, A, and raise it to P minus 1 divided by 2, and do it mod P, if the result is 1, then that number is a quadratic residue. And if you take the same number A and raise it to P minus 1 divided by 2, and do it mod P, and discover that the result is negative 1, then that number would be a quadratic non-residue. Let me just take one example above. This example that we've just done. Let's use this formula to show that 3 is a quadratic residue here. So what does the Euler criterion say? Euler criterion says that you take 3, then raise it to P minus 1. P is 13. Minus 1 will be 12. Then divided by 2, this will be 6. Then you do it mod 13. What do you get? If you get 1, then it means that 3 is a quadratic residue. Let's see what we get. You can use the fast powering algorithm. 3 raised to 1 is just 3. 3 raised to 2 is 9. 1 to go up to 3 raised to 6. So 3 raised to 3 would be 27. Be 27 mod 13. 27 mod 13. 13 is 26. Give us 1. What about 3 raised to 6? 3 raised to 6 is the same as 3 raised to 3 square, which is again 1. So you can see that 3, therefore, is a quadratic residue. Is a quadratic residue. Let's try 5 and see what we get. Let's try 5. 1 to find 5 raised to 6 mod 13. So again, 5 raised to 1 will just be 5. 5 raised to 2 will be 25. Be 25 minus that be 12. Be 12, but instead of writing 12, let's write negative 1 because 12 is a very big number. We don't want to deal with big numbers. We don't want to use a calculator here. 12 is the same as negative 1. What about 5 raised to 4? 5 raised to 4 will be the same as 5 raised to 2 square, which is 1. But what we want is 5 raised to 6. 5 raised to 6 will be the same as 5 raised to 4 plus 2. This is what we know from laws of indices, which is the same as 5 raised to 4 times 5 raised to 2. But 5 raised to 4 is 1. 5 raised to 2 is negative 1. And this is negative 1. So you can see that 5, therefore, is a quadratic non-residue. That's why I said 5 raised to 13 does not mean 5 divided by this does not mean 5 divided by 13. It means the Lagrange symbol. The Lagrange symbol, which means it is 5 raised to 13 minus 1 divided by 2 mod 13. This is what it means. This means this. This means this. It does not mean 5 divided by 13. It does not mean that. And even this 12 is this one. It does not mean 12 divided by 13. What it means is 12 raised to 6 mod 13. That's what it means. The Lagrange symbol. Now, so that is how we use the Lagrange symbol to tell if a number is quadratic residue, that is if it has square root or if it doesn't have square root. In most cases, we are not interested about the square root. We are not interested about the square root. We're only interested to know if that number has a square root. That is our point of interest. We're interested to tell whether it has a square root. But the square root is not our problem. We're not interested with that. So we use the Euler's criterion to determine if it has a square root. Now, you see, we can now tackle even bigger values. We can now tackle even bigger values to determine whether this number, and this number, and this number are quadratic residues mod this. Now, so I'll not go through the fast powering algorithm because we had done it earlier. And of course, these are bigger numbers. You can always use the fast powering algorithm we had learned. But fast powering algorithm is what I've just shown. It's just what I've shown for if you are dealing with the smaller numbers. If you are dealing with the smaller numbers, if it's for examination purposes, we deal with the smaller numbers. Those that somebody can do calculations. But for bigger numbers like this, you require code. But what does this, how do we do this? We just take 27,443, then raise to this number P, 349981 minus 1 divided by 2, and the result, do it mod 349981. That's what I did here. So it will be 27 raised to this, then mod that. So when you do it using the code, you'll then get this. But these are smaller numbers. You can even do it using hand and pen, pen and paper. Yes, you can use Fermat's little theorem and so on. Fast powering algorithm. We have so many tools at our disposal to do this question. Now, so when you do this using a code, you'll find that 27443 is a quadratic residue. And you also try this other one. You also try this. You raise it to that, and then mod this, and again you find it's a quadratic residue. But this one will not be quadratic residue. It will be quadratic non-residue. Even this one will be quadratic non-residue. Now, so the code that I have today is giving you all the numbers which are quadratic residues mod P, all of them. I'm not looking at one at a time. One at a time, you can use the fast powering algorithm, or you can even modify my code to give you one number at a time. But for me, I just wanted one that can give me all the quadratic residues mod P. So it's the one I'm then sharing. That's the code that I have. I've said this Rust code computes all quadratic residues mod a given odd number. And it uses the Euler's criterion. And we've seen what the Euler's criterion says. The Euler's criterion says that if A raised to P minus 1 divided by 2, if this is 1, we are doing it mod P, then this A becomes a quadratic residue. And so those are the formulas then we're supposed to be seeing here, because that is what we are using, Euler's criterion. And I began by saying that our P, we shall use P that is odd prime. Odd prime. So I've begun by saying that if your P is less than 2, if your P is less than 2, then it's supposed to return an error. Supposed to say that the error, and then it tells you that a P must be an odd prime. P must be an odd prime. In other words, what I said this: if P is less than 2, or P on division by 2 gives you a remainder of 0. If P is less than 2, or P on division by 2 gives a remainder of 0, then this code will send there's a problem. Then it returns an error and tells you that P must be an odd prime. So it's supposed to, at the entry point, it's supposed to detect what number you've given it. If it's less than 0, if less than 2, it will tell you something. And if it's a number that is divisible by 2, again, it will tell you that this number is not prime. But if you've given it correct numbers, if you've given it correct P, then it will begin by letting the residues be empty. So it creates an empty vector where it will then be storing those residues. And it's immutable. Mutable, it means this vector will be changing from time to time. The vector begins as empty. Then when a residue is identified, that residue is sent here. So now the vector has one element. When another residue is identified, that residue again is sent here. Now this vector has 2 elements and so on. So how is the code then working? You have given it P, and then let me say P is 7. It knows that the elements mod 7 are 0, 1, 2, 3, all the way up to 6. It's considering the numbers non-zero numbers. This one has already been taken care of. So it's now considering the non-zero numbers, and it's beginning for A in this range. That's what it says. For A in the range 1 to P, and what it understands when it writes 1 to P, it understands P minus 1. It understands P minus 1. So it's counting for A from 1 to P minus 1. In other words, to 6. So it considers 1. Considers 1. Then after considering 1, it finds if 1 is coprime to P. It wants to find out if 1 is coprime. What is the relationship? Let me see. Let's look at this. Or we can go to the example we had just above. Example that we had just above. This example is the one I'm referring to. This example. Now you can see that the numbers here, okay, they are most of them, okay, they are all relatively prime, they're coprime. So that it must be one factor. They're all coprime to 13. Of course, 13 is a prime number, so every number will be coprime. But now, what is it doing? Let's go back and see what it's doing there. Because it's identifying, first of all, if A is coprime. And then, after identifying the coprime, then it must also identify if it's quadratic residue. So A must fulfill these conditions. It must first of all, it must be coprime, then it must be quadratic residue. If that is the case, of course, it's at this point, it's not doing this alone. It's doing it in conjunction with the other functions down here, the other functions. Then if it finds a quadratic residue, it pushes it here, pushes it inside that vector. But it's doing it in conjunction with this other, like this function is the one that is identifying if the number is coprime by finding the GCD. The GCD is 1, then the number is coprime. So this is where it is getting that. So it's working in conjunction with this. So you can see this function here. This function is coprime. This function is coprime. Is this? Is coprime. This is the function is coprime. Then we have this function is quadratic residue. Is quadratic residue. That function is here. So this one is just picking those elements from these functions. Then it picks an element here. That element must be coprime. And then it checks here if that element is a quadratic residue. If that element fulfills these two conditions, if it's coprime and at the same time quadratic residue is stored, is sent to that vector. And then it goes to the next A. So for instance, it must have considered 1, then it goes to 2, goes to 3. Those which do not meet those two conditions are not sent to the vector. But the function that is doing a lot of work, then is this. This is the one that is determining if it's a quadratic residue. And look at the formula. The exponent, let the power. Of course, it begins by saying it wants to find the quadratic residue. If A is a quadratic residue, mod P. If A is a quadratic residue, mod P. Then it says to do this, the power of A, the exponent, will be P minus 1 divided by 2. That is the power. And what about the result? When you take A raised to this power, the result will be done mod P. So it's a mod, then A raised to the exponent mod P. So that is what the result will be A raised to this exponent, and the exponent has been defined here. Then mod P. And then if the answer is 1, the element is a quadratic residue. Else, the element is not a quadratic residue. So if the answer here is 1, the element is a quadratic residue. And if the answer is not, look at this. This is -1. This is -1. Why it says -1 is because, for instance, supposing our P is 13. When we say P minus 1, we mean 12. When you say P minus 1, but 12 is -1. 12 is -1. They mean the same thing. It's not a must that you must use -1 in the formula the way you've been doing. Therefore, you can say P minus 1. P minus 1 is the same as -1. Mod P, just the same thing. Now, so we were looking at what it's doing. It's beginning by defining the power. Then after taking P, A raised to this power, mod P, giving you it's telling you that if the result is 1, then the number is a quadratic residue. Else, if the result is -1 or p minus 1, then it's quadratic residue. Now, if these two are not the cases, then it means that there's an error. Because it must be this case or this case. But if it's not any of these cases, then there must be an error somewhere. The error maybe could be with the code, or maybe with some numbers there. This one is calculated the GCD. The GCD, of course, we know that for us to know if numbers are relatively prime, then the GCD should be 1. So this is what is calculated the GCD, this function. Is find the GCD just to find out if these numbers are relatively prime. And we know how to calculate the GCD. It's saying, for you to get the GCD, is saying you have two numbers A and B, and you want to find the GCD of A and B. It says that the GCD of A and B, for you to get it, you enter this loop and it says while B is not equal to 0, while B is not equal to 0. That is what this means. While B is not equal to 0, come inside here and get the GCD. And you know how to do this. Let me just do it for the sake of those who are not here. How do we get the GCD here? How do we get the GCD here? So let me say I have 6 and 7. And my A here is A is 7 and B is 6. Let me say like that. So it's saying if B is not 0, you come inside here and say let temporary be B. Now case it's 6, temporary. We store it temporarily. We store it temporarily. So you make it 6. Then what is B now? Just a minute. Okay. In this case, B is 7. B is 7 and A is 6. B is the larger one. So temporarily, we store B to be temporary. And then what is B therefore? What is B? So B, we made it to be temporary. Then what is our new B? Our new B becomes the remainder of A on division by B. The remainder of A on division by B. I've mixed this just a minute. let me use bigger numbers. Let me use bigger numbers, slightly bigger, so that you can understand. So okay, A is the bigger number. Let's say 13, and B, let's say 3. So I want to find the GCD. Or let me use a number that can GCD is not 1. Can say a number like 14 and 6. 14 and 6. This will give us a good exercise. Now, so temporary B becomes the temporary, and the new B becomes the remainder of A on division by B. So when you take this A and divide by B, the remainder is 2. This divided by that. A divided by B, the remainder is 2. Now, what about A? A becomes what was temporary. What was temporary becomes A. This is the first the first call. This is the first call. Now we go to the second call. We are doing that until b is 0. This is the condition. While b is not equal to 0, we continue doing this. We only stop when b is 0. That's what it's saying. So the second call, again, we repeat the same thing. Our temporary is b. Our temporary is b. And then what about b? b becomes the remainder of a on division by b. So a is that. When you divide by b, the remainder is 0. Now, so what about a? A becomes what was temporary. Now, when b is 0, you exit. And when you exit, the program says a becomes the GCD. The current a becomes the GCD. So our current a is 2. Becomes the GCD of end. The GCD. This is how you get the GCD using this method. This is how this program does this to find the GCD. So let me share the program. You look at it. And then, of course, there's the recording, so you can always listen to the recording so that you follow. But the main thing for this code is happening here. Is happening here. This is where the main calculation is taking place. Now, this code, this is the code, and this code I told you that I want it to give me all the quadratic residues. It's the same code that I've been sharing in my PDF. So it begins by this point, and then it comes here to calculate residues. And this one is not even calculating. This one is just picking the results from these other functions and then storing them inside that vector. Now, so my main function is here, and I put 13 to be my p, and I want it to give me all the quadratic residues mod 13. In other words, give me all the numbers that have square roots mod 13. Give me all the numbers that have square roots mod 13. When I run the code, it tells me that these are the numbers. So the only number that is not here is 0. So it's all because it was only considering the non-negative, not the non-zero, the non-zero. So we know that 0 is one of the numbers that are quadratic residues. Of course, when you write this code, you can also modify it so that it gives you 0. You can modify it to give you 0. You can also modify it so that you just ask it for a certain number, and then it tells you that this number is quadratic residue. This one is not. It tells you that. I have another one here that gives me the quadratic the numbers. If I wanted it to just give me which numbers have square roots. So I give it a number. For instance, this one, this code, I call it solving quadratic congruences. This one I'm asking it, what are the square roots of 3 mod 13? It's supposed to give me the square root of 3 as 4 and 9, for instance. So I ask, give me the square root of, it tells me the square root of 3. You can see my solution, the square root of 3 is 4 and 9. The square root of 3 is 4 and 9. Mod 13, because 4 times 4 is 16. Mod 13, that is 3. So this one I put it aside. I did not combine the two. I did not want a very long code. Now, so that is quadratic residues. That is about quadratic residues. I want us to look at prime field extensions. Prime field extensions. You have a prime field, and out of this prime field, you come up with other prime fields. That's what you call by extensions. So I've said in algebra and number theory, field extensions are very important concepts. And also in cryptography, field extensions are very important concepts. Why are they important? They allow us to create larger fields that contain a prime field as a subfield. So you have a field, let me say this field F2, F mod 2. You can use this to create a bigger field. You can use it to create a bigger field, where now this one becomes a subfield. So this bigger field, therefore, is what we're calling prime field extension. Is the prime field extension. That's what we mean. Now, so the rest are just notations. These are just notations. K is the subfield. For instance, if you have a field extension by definition would just be this, a pair of these fields. A pair of these fields where one is a subfield of the other. So we are using the subfield to create an extension. You have a subfield, use it to create an extension. So I've given an example. For instance, we have F2. And this F2, you use it to create a bigger field. So this becomes a subfield of that bigger field. Now, we had talked about degrees of polynomials and fields. So the degree of this will be denoted by that. Or the dimension, the degree of the dimension will be denoted by this. This is how we denote it. So when you see something like this, you just asking you, what is the degree? What is the degree of this extension? What's the degree of this extension? That's what it's asking. So that's why I said these are just, they are symbols, but we need to know them going forward. Now let's go to how to construct an extension, finite field extension. How do you construct? You've been given a field. You need to get an extension. How do you get it? That's what is important here. That's what I want us to look at in some few minutes. Given a field, I'm considering this example 153. My field is this, and we know what it means. The question is, can you get an extension of this field? And that extension, I want it to be this. I want it to be F mod 2, then 2. So this is just now the same as F4. It's the same as F4. We had the F2. Can we create F4 out of it? Some books normally use this format. They don't compress it. Now, so what is important here? What does this other two mean? This one we know it. These two, this first two, you know it. is from the field that we initially had. What about this other two? This other two is the degree, of the polynomial. So you see, for you to create F2, you need a polynomial of degree 2. You need a polynomial of degree 2. So this polynomial of degree 2, and it must be irreducible. We had looked at irreducible polynomials. So you come up with an irreducible polynomial, you think of an irreducible polynomial of degree 2. Now, so supposing I've been given this, and I'm asked to create an extension F263, which is the same as F6. So what this means is that I must think of an irreducible polynomial of degree 3. An irreducible polynomial of degree 3. So this becomes the degree of the polynomial, of the degree of the new field. You can also be asked to get this. That means you're talking about a polynomial of degree 4 and so on. Now, so what is important, therefore, how do we create this extension? We've understood what it means, that if you're given f of 2 and you want an extension f22, it means, first of all, you're thinking of a polynomial that is irreducible and is of polynomial 2. But now, that concept of a polynomial that is irreducible comes later. We shall use it later. But at the point of just constructing, this extension, we don't necessarily require this polynomial, but we need to understand that this other 2 is the degree of the new polynomial we're using. You just need to understand that this 2 be the degree of the polynomial we're using. But at the point of creation, we don't require it. Now, so this is where I want to create. So I'll ignore the polynomial, first of all, because we don't require it at this point of creating. So what do we require? What we require is this. Is that I've said here, we want to create F22, which I've said is same as F of 4. The elements of this are polynomials. The elements of this will be polynomials. Remember, the elements of F2 are not polynomials. So these are just 0 and 1. But if you want an extension, and the extension will be F of 2, the elements of this extension will be polynomials. And I've said there will be polynomials of degree 2. But those polynomials should be of this form. The polynomials will be of this form. A plus B alpha. A plus B alpha, where A and B are these elements, 0 and 1. A and B are coming from F of 2, the one you are given initially. A and B are coming from there. So we only need to obtain alpha. And so how do we do this? We use linear combination. We have F of 2 has the element 0, 1. And we want to create A plus B alpha. How many ways can we do this? That's what I'm just asking. How many ways can we do this? A can be 0. And B can also be 0. So if A is 0 and B is 0, what does this equation become? This equation becomes 0. Because it will be 0 plus 0 alpha. Now, the other scenario is that A can be 0 and B can be 1. So we're looking at all possible ways we can achieve this equation using the elements of F of 2. So if A is 0 and B is 1, what does this equation become? This equation becomes alpha. If A is 0 and B is 1. So if A is 0, if A is 0, the possibilities are only these two. That A can be 0 and B 0, or A can be 0 and B 1. The other possibilities that we have is that A can be 1. And if A is 1, B can be 0. So if A is 1 and B is 0, what do we get? What does this equation become? This equation becomes 1. So the other possibility is that A can be 1 and B can also be 1. So what do we get in this case? We'll have 1 plus alpha. So these are the elements of F2, 2. Those are the elements of F2, 2. So we are asked about the elements of F2. So what have we done? We've come up with an extension. We had this field. We had this field that had only these two elements. But we now have another field that has very many elements. And how many elements are these? There are 4 elements. There are 4 elements. You can see that. You can see that this is 4. So the elements there are 0. We have 1. We have alpha, and we have 1 plus alpha. This is our new field, and those are the elements of the new field. And that's what I came up with. That's how you come up with that field, an extension of the field that you are given. Just one more example, just to take to make the knowledge of field extensions to make it understood, make us understand it. Before we can apply it, if we can apply this concept, how do we create an extension? I want to pick another example and create an extension of that. And this time, I've been given this field, F3. And what is the question? Construct an extension F3 raised to 2. In other words, get a field of 6 elements. No, not 6. These are 9. A field of 9 elements. 3 raised to 2 is 9. We've been given a field of 3 elements, but we want to come up with a field of 9 elements. We know what we are going to do. We are supposed to use a polynomial of degree 2. These 2 here. Polynomial of degree 2. And we already know how that polynomial is supposed to look like. That polynomial, by definition, is supposed to be A plus alpha B. That's how it's supposed to look like. So we look at all cases. I'll ignore this for the time being because they're not relevant in coming up with the extension. Because at this point, I just want you to know how to come up with the extension. The extension I've said will be in this format. And we know what f of 3 is. F of 3 been told, and we know it as elements 1, 0, 0, 1, 2. So now, and this is the polynomial we want. So we have the possibility that A can be 0. And we also have another possibility that B can be 0. So if A is 0 and B is 0, this equation becomes 0. The other possibility is that A can be 0 and B can be 1. And if that happens, we get alpha. We can also have A being 0 and B being 2. If that happens, what do we get? We get it to alpha. Get it to alpha. So if A was to be 0, we have exhausted all the possibilities. We exhausted all the possibilities because A can be 0, B can be 0. A can be 0, B can be 1. A can be 0, B can be 2. Now, the other possibility is that A can be 1. And if A is 1, B can also be 0. And this equation gives us 1. We can also have A as 1 and B as 1 as well. If that is the case, then we have 1 plus alpha. 1 plus alpha. That's what the equation gives us. We can also have A being 1 and B being 2. That's another scenario. And if that happens, what do we have? We have 1 plus 2 alpha. 1 plus 2 alpha. So we have exhausted possibilities if A were to be 1. So what about A can also be 2 and B 0, A2, B1, A2, B2. Again, you find the other possibilities. So how many possibilities are those? 1, 2, 3, 4, 5, 6. And again, we said A can be 2, B can be 0, A can be 2, B can be 1, A can be 2, and B can also be 2. So those are 9. You come up with nine elements. So the first element will be 0, you have that, you have this, you have this. Those will be 9 elements. You have 9 elements, and this, therefore, is the field extension of F3. This is the field extension of F3. What is interesting is that this field extension also forms a field. It forms a field. In other words, we should be able to know that when we add any of these two elements, you get an element here. And when you multiply them, again, you get a member of this set. When you add them, you get a member of the set. When you multiply them, you get a member of this set. Adding them is very easy. What is interesting is how do you multiply? But adding them is very easy. I've taken an example. I've taken an example of how to add. I want to add this element, alpha plus 1. No, I've taken an example of how to, yes, alpha plus 1 plus 2 alpha, 2 plus alpha. What is that? This 2 plus alpha. Now, you just add the unlike terms, the like terms. And when you do that, you get 3. You get 3 plus 2 alpha. But remember, we are doing it mod 3 because we are dealing with the f of 3. So what is this? Mod 3. It becomes 0. 3 becomes 0. So then you arrive at 2 alpha as the result of this summation. The result of this summation is 2 alpha. And you have seen how the 2 alpha has come about. 2 alpha has come about. What is that? Yes, 2 alpha. This is now to multiply is a bit interesting because first of all, you must now define the polynomial you're working with. For you to be able to multiply this, you must tell the polynomial you're working with. So that is why I skipped the upper part because it was not important. But now I can come back and define my polynomial. The polynomial must be irreducible. There's no formula in coming up with a polynomial. You only have to come up with a polynomial that is irreducible. That's the only requirement. It should be irreducible. So I thought that this would be irreducible. So what I was trying here, I was trying to find out whether it's irreducible. In other words, whether it lacks factors. So, but coming up with this, it doesn't need to be this. There can be any other, but you only need to prove that it's not reducible. So I chose this polynomial. Then I was now checking whether it's reducible. I discovered it was irreducible. This is a polynomial I'm working with, therefore. Now, when it comes to multiplication, this polynomial then works, it comes in. And each person will have his own polynomial, but the results, at the end of it all, the results will be the same. They'll be similar. Now, let's now multiply. We have known the polynomial we're working with. I want to multiply these two. Now, when you multiply these two, what do you get? This gives you 2, and this gives you alpha. This gives you 2 alpha, and this one gives you alpha square. So what do I have? Let me just write what I have. I got 2, I got alpha, I got 2 alpha, then alpha square. That is 2, write it here, 2. Then I got alpha and 2 alpha, which is 3 alpha, and then plus alpha square. But the 3 alpha, of course, we know we are dealing mode 3. This becomes 0. So we have 3 plus alpha square. What about alpha square? What about, oh, this is 2. This is 2. But what about the polynomial? The polynomial working with this x square plus 1. This is a polynomial working with. So it's in fact the same as alpha square is -1. It's the same thing. Alpha square is -1. So where there's alpha square, you put -1. So this becomes 2 minus 1. Which is 1. So I multiplied this, I multiply those two, and the result you get is negative. You get is 1. You will always, even you will have made this one, you will have made this one 2. Because you are doing it mode 3. This one becomes 2. So what it means, it will be 2 plus 2, which is 4. Mode 3, again, you get 1. So also, that's how you multiply. But multiplying means you have to, first of all, define the polynomial. So I think when we meet next week, we'll again go through this field extension, especially the multiplication part, so that we draw the tables, because I wanted also to draw the tables for addition and multiplication. But before that, you need to know how to multiply. So these tables I was drawing just to prove that the field extension is also a field. Is also a field. That's what we do. So you must show that it fulfills all the axioms of a field and addition and multiplication. So that's what I wanted to do. So maybe next time we begin with that before we proceed to the next topic, because I wanted that next week we can look at a different topic, because we're coming to the end of these fields, so that next week we look at a different topic. Thank you. Any question?